In
Let us start our class. Let us hope that others will join soon. In the last class, which you attended in the week before the last week, we have started our chat module on torsion. I am just narrating you what do you mean by torsion or twist or couples. Actually, a shaft is a member. A shaft is an example of a member in torsion. What do you mean by this one? What this type of shaft is meant for, what work they're supposed to do, what service they're giving us. They're transferring power. They're used to transfer power from one point to another. Say from a motor to a machine tool. Say from an engine to the rear axle of the automobile. From motor engine to the rear axle of the automobile, we are transferring power through a shaft. From a motor to another machine tool, we are transferring power through a shaft. Say a steam or electric or turbine, from a steam turbine or hydraulic turbine, or we are transmitting power to an electric generator through a shaft. This is the shaft we are using for transmission of power of various resources to various receiving end, or various resource end to various receiving end. Resource end can be the engine of a car, can be a turbine, and can be a motor, and the end servicing end and receiving end can be a machine tool, can be a rear axle of a field, can also be a electric generator, can be any other example. There can be so many examples about the resource and about the receiving equipments. Now, the shafts, we are using shafts, which is nothing for this type of transmitting power, or which can be pure twisting couple, which can be a pure twisting couple, or a torque acts over it over the polar axis. So we use shaft to transmit power, and how we transmit power? We by using a twisting couple or torque over its polar axis. Due to the action of this twist or couple, a shear stresses are developed perpendicular to the radius of all the transverse sections. So you have to develop a shear stresses and across the perpendicular to the radius of all transverse section. As a result, complementary shear stress also developed in the longitudinal planes, and which causes a distortion of filaments. And as the cross section across the transverse plane is symmetrical, the points remains under same radial distance before and after the twist. The angle of twist recounted about the angle of shift. So what we are doing here, the shear stresses. We are developing shear stresses due to the action of shaft, due to the action of torque. Just 1 second, please. Where is that point code? Now, what we are doing here, see the text grow. No, it's not okay, but yes. So what is going on? You could talk, talk, twist, you to talk, twist, and couple on a shaft. Actually, on a shaft. On a shaft, we have developed shear forces on perpendicular to the axis of all transverse section, which is perpendicular to the axis of all transverse section. What is transverse section? Transverse section means it is a section taken perpendicular to longitudinal axis. Longitudinal axis. So this is developed, that's the shear forces acting perpendicular to the axis of all three transverse force, axis of all transverse section. So the axis of transverse section will be along the longitudinal axis itself. So as a result, a complementary shear stresses are developed to the longitudinal planes, which cause a distributional flare. So along the longitudinal planes, plane means planes along the longitudinal axis the planes along the longitudinal axis, shear stresses are developed. Actually, it is a complementary shear stresses. Complementary shear stresses are developed. In order to resist this transverse shear stress. So shear stresses are developed. Stresses are developed along the longitudinal axis. Now the axis as well as along transverse section. So what is shear stress? You know, the stresses of the forces which is acting along any surface is defined as the shear force acting over the surface. So we are having shear force along the longitudinal axis as well as along the transverse section. These are complementary to each other. They are same. It means these shear forces are complementary to each other. Means it is of same magnitudes, but in opposite direction, but acts in opposite direction. Opposite direction, but they are parallel to each other. Also, they are parallel to each other. Next, we are going to something else. Now, as the longitudinal section may be transverse, is symmetrical. As the cross section across any transverse plane is symmetrical, the points remains in the same radial distance before and after the twist. The angle of twist is according to the length of the twist. What is the cross section for any transverse plane? Means planes across the normal to the longitudinal axis. Is symmetrical. Means they are same. They are same in as per the axis. They are same in all sides. The points remains at the same radial distance before and after the twist. You see the points of all the different points before the twist and after the twist remains in the same radial distance. They will move along the radial direction, but not in the longitudinal or radial. Longitudinal, they will not move along the radial direction, but will move along the transverse direction, and it will after the twist. The angle of twist is general. It also recommended over the length of the shaft. This angle is recommended over both length as well as cross-sectional area. Now there are certain important assumptions are made. What is this? The material of the shaft is supposed to be homogeneous in nature, isotropic, and perfectly elastic. This is homogeneous, which is it is same. Contents is same in all the neighboring points. And isotropic, it is same. The property is same in all three mutually perpendicular direction, and they are perfectly elastic. Means they go back to the original position after the load is removed. So here, loading it within the elastic limit. Loading within elastic limit. Now, this material obeys Hooke's law, and the stress remains within the limit of proportionality. Means this material obeys Hooke's law. Means as per Hooke's law, stress is directly proportional to strain. Means the deformation per unit length is directly proportional to the resisting force per unit area. And this material, all the material obeys this Hooke's law. And the Hooke's law, as one important condition of the Hooke's law, is it material should be plastically elastic. Perfect elastic means it should be loaded, and it should be loaded within the proportional elasticity, and it should be perfect elastic means it is supposed to be after loading, if the load is removed, it will go back to the original shape. And so it is evident that you are supposed to load the material within the elastic limit, not beyond it. The twisting couple act in the transverse plane only. The torque only transverse planes acts only the transverse plane. Twisting couple, torque or moment is acting only on the transverse planes, means only on the planes which is at normal to the longitudinal axis. All radius remains straight after torsion. Means after you twist, radius, the length of the radius will not change, and length of the radius will not be distorted. And parallel planes remains parallel planes normal to the axis, does not wrap or distort of the torsion. So all the transverse planes which are normal, which are parallel to each other, will remain parallel and will not be disturbed or wrap after the before and after the twisting. A cross section at any axial section at any axial length rotates at a rigid plane as a rigid plane, that is all diameters of the cross section rotates through the same angle. A cross section often at an axial length rotates at a rigid plane, or diameter rotates in the same angle, which means a particular cross section remains rigid, means all the diameters rotates together. So there may be infinite number of diameters in the cross section. All the diameters rotate together by the same amount and by the same angle. These are the 6 important assumptions made during the action of thing. All these things are important because all these assumptions are important because all our subsequent reactions will be discussion will be based on the fact that material property of the material is same in longitudinal and in all 3 mutually perpendicular directions. This material will obey Hooke's law, means remains perfectly elastic, and the stress will directly proportional to strain. All the radius remains straight before and after the torsion. All the planes, cross-sectional planes remains parallel to each other, will not disturb, and all the cross-section will be perfectly rigid, which means all the radius will move in the same, in the same angle, so when it is rotated.
আচ্ছা ঠিক আছে ঠিক আছে বাস আছে না ঠিক আছে ভাই এখন তো পয়সাটা পেয়েছে আবে পাঁচবে গুগল পে খুলে তো রাখেন জি দেখ
Now, let us go for the analytical discussion of the twist or the circular shaft. So what we see, we are having a circular shaft, means this cross section is a perfect circle. It's of certain length, say L, and its diameter is D, and radius is R, and it is acted upon by a torque T. So what we have the length and diameter, and we have the external applied torque or twist equal to T. The shear strain. Hello. Now, the shear strain phi of the elements at a radial distance r from the axis is constant for a particular value of t. And what is shear strain? This is the shear strain of the elements at a radial distance. Say here is the radial distance, this is the radius, this is the center, and this is radial distance, which is creating radial distance from the axis. It is the shear stress. What is means the deformation by means of the shear force remains is constant for a particular value of t. So for a particular value of dot, their shear stress means shear strain means the deformation due to the shear is remains constant. So that's what happens. Here is a line OA is twisted by the angle OB. Here it is twisted from line OA is equal to twisted by an angle theta and twisted to out to the position OB. Now theta is the angle of twist over this cross section related to another cross section at a distance L apart. Then arc AB, this is given in this form. You see, due to the action of twist, this the radius OA is twisted to the radius OB, and in the surface also, if we take fuses from the longitudinal axis, you'll see it is also moved from the position A to the position B due to the angle of twist. We are assuming that across the radius it is twisted by an amount theta, and across the longitudinal length it is twisted by an amount phi. So what we are having is like this. The arc AB is equal to r into theta is equal to L into phi, which is arc AB. This is the arc AB here in the longitudinal length from here to here, and also from here to is visible from here to here. This arc is given by is equal to the radius r multiplied by this angle theta, as well as the length, which is also equal to the length L multiplied by the longitudinal deformation phi. So r into theta is equal to is given as L into phi, or the arc AB or phi is equal to, we know, the tau divided by g. As we know, the shear strain phi is proportional to shear stress tau, or tau is equal to the modulus of rigidity multiplied by the shear stress tau. Sorry. Tau is proportional to the phi, means shear stress is proportional to shear strain, and shear stress is equal to G into phi, or phi is equal to G dt tau divided by G. So if we put this value of tau divided by G in place of phi, this equation will become r into arc AB is equal to r into theta is equal to L into tau divided by G, or tau divided by r, it will become G into theta divided by L. So if we put the radius r in as a denominator here, denominator of the tau, so tau divided by r is equal to becomes this G into theta divided by this L. So tau by r is equal to G into theta divided by L. Now the tangential force on the element will be tau multiplied by the cross-sectional area of the element. So it is at the radius r, the circumferential length is 2 into pi into r, and the thickness is the radial distance is the distance in the radial direction is in elemental radial direction is equal to dr. So tau multiplied 2 into pi into dr is the tangential force on the element. The moment of this tangential force will be the tangential force multiplied the radial distance, which is equal to r. So tau 2 into pi into r into dr multiplied by r. Thus, the sum of the moments of all the for the whole surface, tau multiplied by 2 pi r into dr into r. It is the integration of the whole amount. Thus, if we put the value of tau here, we will have g into theta dr by L into R, is 2 into pi R into dr into R, or as g into theta by L is independent of dr, we put it outside the angle of integration and makes it 2 into pi R dr into R square, or integration of 2 pi R dr into R square is the polar moment of inertia of the shaft, defined as the polar moment of inertia of the shaft, which means the area of the particular element, particular round element, circular element, multiplied square of this distance from the center. This is the definition of polar moment of inertia, which we have discussed in the last class. So we put the value of J here, it becomes, and the integration of the whole thing is the polar momentum, total polar momentum of the full shaft. So this will become G into theta by L into integration of 2 pi R dr into R square. So we put J in case of J instead of polar momentum of inertia and put the value of J here. So equation 6 becomes T into T divided by J, G into theta by L, which is actually T into theta by L is actually equal to tau by R, and this becomes T divided by J into tau divided by R into G into theta divided by L. This is shown for a given shaft, shear stress is proportional to radius. This is shows that because tau is proportional to the radius, it is changes according to the radius we have chosen for that. Now here we show that in this figure, the shear stress distribution in a solid shaft of radius R. The major outside radius is of a solid shaft is R here, and this is the shear stress distribution. It is 0 at the center, and it goes up tau max at the outermost radius. The stress distribution of hollow shaft here is of inner radius R1 and outer radius R2 is given here. It is 0 at the center of the shaft and have certain value, and minimum value at the time minimum is the innermost radius of the shaft, and maximum value at outermost radius of the shaft. And for solid shaft and hollow shaft, the tau max or the maximum shear stress is on the outermost radius, and 0 at the innermost radius. And for the hollow shaft, it is also have a minimum value Ri at the innermost radius of the shaft, but that is not equal to 0. Now, the equation is analogous to our equation for bending moment, or the equation for bending, as where T divided by J corresponds to M divided by R, and tau divided by R corresponds to sigma divided by I, and G into theta by L corresponds to E by R. As we know, the polar moment of inertia J is equal to Ix plus Iy, means the moment of inertia along x-axis and along the y-axis. For circular shaft, it becomes Ix and Iy. In both the cases, it is same. So it becomes I by 64 d to the power 4 plus pi by 64 d to the power 4, which is equal to, for circular shaft, pi by 32 d to the power 4. Thus, for solid and hollow shaft, the following discussion can be solidly made. If we put the value of J in the moment of equation, we'll find that tau divided by pi d to the power 4 is pi d tau divided by pi d to the power 4 multiplied by d by 2 divided by 32. Here we put the value of J here and put the value of radius here, which is equal to d by 2, and put the value of J here from this equation, pi d to the power 4 by 32. So in this becomes maximum stresses become 16t divided by pi d to the power cube, which is also at the outer surface. For hollow shaft, the D and for hollow shaft, D and capital D are the outer inner diameters respectively. So, then J is equal to pi d to the power 4 minus d to the power 4 minus capital D to the power 4 minus small d to the power 4 by 32. If we put the value of J here in this equation of torsion, and we'll put the value of R is equal to half of the maximum radius, d multiplied by d divided by 2. So pi d to the power 4 minus d to the power 4 divided by 32, or 16t into capital D divided by pi capital D to the power 4 minus D to the power 4 at the outer surface. So the maximum stress and both the hollow and solid shafts are at the outer surface, and both are given in terms of the outer radius and inner radius respectively. Next, the torsional moment of resistance or resisting torque. How much resisting torque is being created, which is of most importance to us. The maximum torque which can be carried by a given section of the shaft for a given maximum value of shear stress is known as torsional moment of resistance. The maximum drag which can be carried by a given section of the shaft for a maximum value of shear stress is given as the torsional moment of resistance or resisting shaft. What is means? What is the max? First, we have to find out the maximum value of the shaft and maximum value of shear stress, and we have to find out what is the maximum value of torque which can create this amount of shear stress. And this maximum value of the torque will be defined as the torsional moment of resistance or the resisting torque. So first, the maximum shear stress. Next, we have to find out the maximum torque which makes this shear stress. And this maximum torque, which is defined as torsional moment of resistance or resisting torque. It is the sum of the moments of tangential stresses, shear stress acting on any transverse section. So it is the sum of the moments of all tangential shear stress of any shear stress on any transverse section. J divided by R is defined as torsional or polar sectional moment. If we divide or the moment of inertial diameter of the radius of the shaft, you will get that polar sectional moment. Torque per unit radian twist is defined as torsional stiffness. So per radian twist. So how we will note that exercise? We have to find out the ratio T divided by theta, which is also can be equal to J, means polar moment of inertia of the section, multiplied by the modulus of rigidity and divided by the length. The parameter G divided by J known as the torsional rigidity of the shaft, similar to flexural rigidity of the beam. So J into J is given as T divided by theta by L. Thus torsional is also the torque per unit angular twist. This is the per unit angular twist, means the angular twist per unit length. The angular twist per unit length and torque divided by this angular twist per unit length is given as the torsional rigidity, or also given as G into T into J, as per our definition, as the parameter G is the torsional rigidity. So we have got four important definitions: torsional or polar section, polar sectional moments, a torsional moment of resistance, First of all, known as torsional or polar sectional moment, which is that defined as the polar moment of inertia divided by the outside radius. Then torsional stiffness is the torque given by per radian twist. Torque is the T divided by twist is per twist in radian is divided by is equal to theta. So T divided by theta, or T we can replace them as J into J divided by L from the torsional equation. The parameter J into J is known as torsional rigidity, and is defined. This parameter J into G is the torsional rigidity, and it is given by T is equal to T divided by theta by L. The torsional rigidity is also torque per unit angular twist. If we can have this from this equation, that is T multiplied by length divided by theta is equal to J into G, or J into G is equal to T divided by theta by L. So this becomes the equation for torsional rigidity, also for the torque per unit angular twist. Next, let us go for the power transmitted. The shafts to transmit the maximum power from the point of generation to the point of its application. shafts are the medium. Which is the medium to transmit power? I have told you in the beginning of this lecture that it is the medium of transmitter power from the motor to the transmitter power to the point of application. Means transmitter power from motor to the say lathe, or from the engine to the actual to the real wheels of the motor, etc. The power transmitted is the watt turn per second. Thus, P is equal to T divided by omega. P is equal to T divided by omega is equal to T multiplied by 2 into pi into n divided by 60. So we know the power is the torque transmitted multiplied by the power is the torque transmitted T divided by the radial speed per unit per second, radial speed per unit per second, which is equal to 2 into pi by n divided by 60. And so this equation becomes 2 pi n by t by into t into divided by 60, where t is the applied torque, n is the RPM or revolution of the shaft in RPM. A shaft may transmit power at more than one section to different machines. Transmit at more than one section to different machines. So throughout the length, a shaft can transmit power from different position of the length to different machines. Also, the shaft may be subject to different torques and different sections. Thus, the torque exerted on the shaft can be different from section to section. In such case, the principal conservation energy will be applied. Usually, the shafts are designed on the basis of limiting the value of stress and the angular deformation. Next comes some problems. Analytical problems. What is given here? A solid shaft with transmit 100 kilowatt in 150 RPM. So what is the power transmitted is given, and what is the RPM it is rotating is also given. Determine the suitable diameter of the shaft if the maximum torque transmitted exceeds the mean by 20% of each direction. So, and the shear stress not to exceed RPM 60 MPa, and also find the maximum angular twist or in a length of 4 meters of the shaft. Now, of shaft G is given as 80 MPa. So what is given? The power supposed to transmit by the shaft is given, and RPM, which is RPM, the speed with which the shaft is moving, that's also given. But we are supposed to find out the suitable diameter of the shaft to transmit. So what is the maximum torque transmitted but exceeded the mean by 20% for each revolution? So we have to find out what is the maximum torque is being transmitted, and we have to increase this mean torque by 20%, so that we can take into account all fluctuation of the load, and we have to find out the diameter according to this maximum torque. The shear stress allowable is given here 60 MPa, and the maximum angle of twist is given of 4 MPa m of the shaft. G is equal to 80 GPa. Let us close the meeting and come in again.